We have seen that there are two ways in which we can create a detonation, or let us say form a detonation. In the first method, we deposit some energy rapidly at some source, some energy exceeding some threshold value. We form something like a strong shock wave. We ensure that this strong shock wave is formed at some distance away from the source. The time of formation should be such that chemical reactions get completed. If the shock wave is sufficiently strong, the chemical reactions which occur behind the hot zone of the shock wave, there is a temperature increase in the shock wave, and if this temperature increase is quite large, corresponding to the large Mach number, this chemical reactions will drive the shock wave and you get a detonation wave. This we say is a direct method of forming a detonation, and this is known as the direct method of initiating a detonation. That means you form a blast wave, the blast wave couples with chemical reactions, the chemical reactions take over and drive the detonation as it is. This is also known, since we form a blast wave, it is also known as the blast initiation of a detonation. In the second method, what did we tell ourselves? When we deposited the energy source, the energy release has not been sufficiently rapid, and what you form is a flame. A flame moves at a few centimeters per second, and as the flame moves, what does it do? It is something like a piston which compresses the unburned gases ahead of it, and therefore, the velocity of the gases ahead of it increase, and therefore, what happens is the flame speed in the moving gases increase, and not only that, when the gas velocity is increased, maybe the turbulence increases, the intensity of turbulence increases, the length scale changes, and therefore, you form something like a corrugated flame. Compared to a few centimeters per second or a few meters per second, this velocity is much higher because it is a turbulent flame, and ultimately this turbulent flame again drives the gases ahead of it, just like an accelerating piston pushing the gases, and therefore, I have a highly turbulent, highly wrinkled type of a flame which is formed. We also saw some pictures saying that whenever I have blockages or the wall effects, I create, since the velocities ahead of the unburned gases are already large, I create shock structures or maybe expansion waves, maybe weak shocks within it, which make the turbulence so high that maybe the when something is there, this is the unburned gases in which the concentrations are high. Whenever something starts burning, because of the high turbulent intensity, the chains which are formed are also terribly fluctuating or terribly mixing, and therefore, what happens is I could have a zone of gases which are formed ahead of the flame, which goes into something like a constant volume combustion. When you say constant volume combustion, it is as if the whole thing is just burning, as it were, and therefore, at constant volume I can say, well, it is something like a sonic combustion which is taking place, and this type of a flame brush in which you have intense turbulence, that means I have a very intense turbulent flame brush which is moving at extremely high velocities of the order of the sonic speed itself, but still it is not a detonation. This can, when the chemical reactions time are such that it is able to now form a shock wave, if it is able, because now it is able to form a shock wave, it can couple and form a detonation. Alternatively, if I have these wrinkled flames, the length scale also is somewhat larger in the intensity of turbulence, and these wrinkled flames, supposing they hold together some unburned gas mixture, and this unburned gas mixture is now being burned from the outside towards the inside, it collapses as something like an implosion takes place, and you form a shock wave, and therefore, behind this shock wave chemical reactions occur and you get a detonation. Well, this is an indirect way of forming a detonation, and this is how in most of the accidental explosions, this is how a detonation gets formed, and therefore, you form a flame which transits ultimately into a detonation, and the distance taken from the source to form a detonation is what we call as the run up distance. That is, this is an indirect way of forming a detonation, which we said is deflagration to detonation transition or flame to detonation transition. In some cases the run up distances are quite small. Even though you form a flame, the run up distance could be small, and we must not mistake these two types of initiation. Therefore, we tell ourselves, well, a detonation could be formed either as a blast initiation or directly, or as a deflagration to detonation transition. Having seen the way in which you have something like a compression behind a detonation compared to expansion behind a flame, we would like to examine a little more about what this detonation looks like. Now, to be able to see that, I show a few slides, and it is seen that maybe detonation is not a smooth shock with chemical reactions occurring behind it, but it is something more than that. Let us take a look at one or two slides and try to see how a detonation once started propagates. In this picture, see, this is the direction of propagation of a detonation, this is the unburned gas mixture, and what is it we see? We see some lead shock here, you have one lead shock, you have another lead shock here, another lead shock here. That means the front of a detonation is not as smooth as we thought it is. It consists of multiple shocks, and also behind the shocks you also find I have waves behind the shock as well. I have some wave here, I have some transverse wave here, I have a wave which is normal to the lead shock over here, which means that the front of a detonation, just like what we presumed here. What did we presume? I have a detonation front, a shock front, I have chemical reactions occurring over here, and what is it we see? Well, there are multiple shocks in the front, there are also waves behind it. That means I have something like a transverse wave, I have lead shock waves or the front detonation waves. A detonation seems to be something like a multiple shocks which are there in the front, which are there lateral to it, maybe these things move in this particular direction, and therefore, if we now say, well, a detonation is something like a multi-headed shock front or a multi-headed detonation wave, and therefore, maybe we should take a look at this before I start working for the velocities and pressure behind a detonation. Therefore, let us try to simplify this picture and see what it will look like. Well, the front of a detonation we say consists of shocks. Well, I have a shock over here, I have another shock over here, these two shocks at the intersection point, I have a third shock over here, and these three shock interactions we have seen earlier when we were looking at blast waves. We talked in terms of Mach reflection. When two shocks interact at a very shallow angle, well, it is not a regular interaction. That means incident wave is not reflected as a reflected wave, but you get a third shock, you have a standoff shock which we called as a Mach stem shock. We have something like a Mach wave reflection, and the front of a detonation consists of a Mach stem shock and another shock which is known as an incident shock, and you have a lateral shock which is known as a transverse shock. This is how it looks in a two-dimensional format. Maybe at the intersection of the three shocks over here is what we call as a triple point. Now, it so happens that the lead shocks, maybe the Mach stem shock and the incident shocks, of these two shocks, the Mach stem shock is much stronger than the incident shock, with the result the induction time or time for chemical reactions behind the Mach stem shock is somewhat smaller, while behind the incident shock it is much larger. In fact, the transverse shock takes the gases which are still reacting, and maybe some chemical reactions occur over here. Therefore, the front of a detonation is not something like a single shock wave behind which chemical reactions are occurring, but you have multitude of shocks. And therefore, if I were to enlarge this picture for the total detonation, what is it I get? Well, I had the Mach stem shock, I had the incident shock, I have the lateral transverse shock over here, and what is happening? The chemical reactions, the Mach stem shock is normally much stronger than the incident shock. Therefore, the chemical reactions take smaller time, the induction time is smaller, followed by the chemical reactions. Here the induction time is much larger, and behind the transverse shock again some chemical reactions are taking place. Behind this you also have the slipstream or the a zone separating the gas is processed here and the gas is processed here, you have something like a shear layer, and therefore, what is going to happen? I have vorticity at this particular intersection point, and therefore, when a detonation wave propagates, what is happening is this particular point, that is the triple point, is capable of, if I put a sort of a paper coated with some material like, let us say, soot or some substances which can easily be written upon, like I have a paper on which I put some carbon deposit and I scratch on it, I can easily write on it. So also this point O, which has high vorticity, can write on a piece of paper, and if I look at it, I find that my shock trajectory, that means the triple point, traces a curve something like this, it traces a curve something like this. If I were to start earlier, well, the triple point traces a curve like this, comes back over here, the next triple point corresponding to this has traced this curve, comes like this, traces this curve, comes like this. That means I have something like these cells which are being formed, and these cells are very much characteristics of a detonation. Therefore, let us again review this. We say that the front of a detonation consists of a mark stem shock. The mark stem shock is strong, the chemical time behind the mark stem shock is smaller, the incident shock is weaker, the chemical time behind it is larger. You have a transverse shock, behind the transverse shock also chemical reactions take place. And how do these things propagate? Maybe let us start with the point here, and this triple point comes over here, the triple point comes over here, the triple point meets, that is this triple point and this triple point meets over here. That means the transverse wave over here and the transverse wave over here hit together over here, and once it hits, well, I have another cell being formed or regenerated, and therefore, I have a mark stem shock which is being formed here. This mark stem shock keeps progressing as I am showing, and once the center of the cell is reached, what happens is the mark stem shock during this period of movement keeps on decreasing in strength, and it becomes something like a weaker, something like an incident shock. But in the neighboring cell, what happens is, well, this is the mark stem shock, it comes over here, becomes weak, something like an incident shock, and in the neighboring cell over here, the another interaction takes place, a mark stem shock is formed, and therefore, I have a mark stem shock followed by incident shock followed by a mark stem shock, and this is the way a detonation progresses. Within each cell of detonation, as I just now told, maybe at the intersection point I form a mark stem shock. This mark stem shock is continually decaying. Surrounding this particular the mark stem shock, I have an incident shock, and this incident shock with transverse waves comes and hits here. This is also decaying. At this point, a new mark stem shock is created, and therefore, the picture of a detonation being a regular sort of a one dimensional constant velocity front which moves does not seem to be true, and in fact, what we have is within each cell of this detonation, see, we said we form these cells of detonation, and these cells are trajectories of the triple point, and therefore, within each cell of a detonation, I have the lead shock, which is a mark stem shock with which a cell is being formed. This continually decays, and when initially I have a mark stem shock which is very strong, behind it chemical reactions occur rapidly because the induction time at high temperature is very small. As it keeps decaying, well, what happens, the induction time, I show the zone of chemical reactions by black line over here. This is the zone of chemical reactions between the shock front and the chemical reaction. There is a zone or induction time, the time taken for the reactions, and as the shock decays, this tends to decouple from it, and then this shock further decouples, it becomes an incident wave, and it further reduces in strength, and therefore, I have totally decoupled reaction, but then the transverse waves come and hit at this point wherein the triple point intersects and a new mark wave is generated. Therefore, the procedure by which a detonation propagates is, well, I have the triple point intersection over here, I have a mark stem being formed, behind the mark stem rapid chemical reactions are occurring. I am just considering the events within a cell of detonation. We will take a look at the neighboring cells shortly. Within the mark stem, well, chemical reactions occur rapidly, it drives it, but during the process of travel, the mark stem shock decays in strength, maybe it starts with a strength which is around 1.2 to 1.3 times the mean value of the Mach number at which it is proceeding. It decays down, it reaches a value over here, and then it further decays, chemical reactions get coupled, it further decays, and by the time the two triple points or the transverse waves intersect, it has decayed in strength to something like 0.6 to 0.8 times the mean Mach number at which the detonation propagates. Therefore, in the adjacent cell, well, over here I have incident waves, that means I have the triple point intersecting here, again a Mach stem shock being formed gets into the incident shock wave, and therefore, the front of a detonation consists of a Mach stem shock, an incident shock in the neighboring cell, in the neighborhood of the other one it is the Mach stem shock followed by incident shock, and this is the front of the detonation. If I were to consider a single cell, if I were to consider events within a single cell, maybe this cell followed by the next cell of detonation followed by the next cell of detonation, what is it I get? I get maybe at the point of intersection of the triple points, that is the two transverse waves intersect, all of a sudden there is a increase in the Mach number to from a mean value to something like 1.2, 1.3 times the mean Mach number, and within the cell the Mach number keeps decaying, it reaches a value between 0.6 to 0.8 times the mean value, and again it spikes up, again it drops in the next cell, and therefore the detonation is not something which is moving at constant speed throughout, but within each cell it is sort of something like a pulse, it is sort of galloping, starts from the high value, comes down to a low value, goes to a high value, comes to a high value. Therefore, it seems to be propagating in spurts. This is the two-dimensional sketch, and if you were to look at three-dimensional, well, it is possible, but only thing is that this particular diamond pattern gets into something like a fish cell pattern. Well, we have to take a look at that, and therefore, if I were to take let us say a pipe, in this what I am showing is I have a pipe containing some explosive gas mixture. I show this pipe at different instants of time. I have a detonation wave propagating, the detonation front is over here initially, and therefore, see behind the detonation front, as I said, the triple point can write on the wall if the wall can be made to contain some material on which something can be written, like I have a smoke foil or something like sand which is embedded on the wall, I get this particular pattern. As the detonation wave propagates, well, these scale structure or this cell structure propagates, and you see the front of a detonation is associated with all these structures, and you have this structure which is characteristic of a detonation. The front propagates, and what is the front? The front consists of all these myriad of the lead shocks, you have the transverse waves behind it, and therefore, the front of a detonation is not something which is a beautiful one-dimensional or let us say a planar shock front, but it consists of a series of lead shocks followed by transverse shocks. That is, it consists each shock interaction consists of three shocks, namely the Mach stem shock, an incident shock, and a transverse shock. Having seen that this is the structure by which detonation propagates, just to illustrate the three dimensionality, if I were to go to the previous slide and then I were to put something like on this particular surface, I put a paper on which the signature could be written. Well, the signature is not only in this plane which I am showing, but it is also normal to it. That means, I get the site of pattern corresponds to the diamond structure, and therefore, we say, well, within the cell of a detonation, what happens is I start with a high Mach number. At the end of the cell, the Mach number decreases, again I have a spurt, starts with around 1.4 to 1.2 times the mean Mach number, comes down to around 0.6 to 0.8 times, again there is a spike. It seems like in spurts the detonation propagates, and detonation propagates within a cell of a detonation. You have the neighboring cell over here, you have other cells, and these detonation cells are very much a characteristic of a detonation, and these cells are also known as cells of detonation. Let us take one more look at this particular cell. Well, you have the triple point coming along this trajectory, you have triple point coming along this trajectory, you have transverse waves over here, the transverse wave intersect over here, it starts a Mach stem shock, it comes over here, it decays in strength, becomes an incident shock wave, and then the writing of the triple point is along this trajectory, the triple point and the corresponding transverse waves intersect here, another cell is born over here, and this is the way from cell to cell the detonation wave propagates. Therefore, a detonation wave is a multi-headed structure, and this cell of a detonation is something which is very much characteristic, and we say, well, this is the length of a detonation. The width of the detonation cell is called the cell size of a detonation, which we characterize by the word lambda, by the letter lambda. Therefore, to sum up, a detonation wave is not something which is beautiful one dimensional, but it has a structure, it has a particular characteristic structure which is known as a detonation cell, and it is characterized by a particular dimension lambda. This particular cell size is characteristic of the explosive gas used, its pressure, its temperature, its physical properties, its rate of reactions, and for gases which are very reactive, lambda is very small. For gases which are not that reactive, in which the mean velocity of detonation is slower, the value of lambda could be large, and there is sizable variation in lambda. And if I were to just put this is Shepard's data, and if I were to say, yes, measured cell width as a function of the equivalence ratio 1 corresponds to stoichiometry, and you find there, if I talk in terms of hydrocarbon mixtures, the cell size could be as much as something like 4 to 40 centimeters, depending on the conditions, depending on the equivalence ratios. But if I were to take hydrogen air mixture, the cell size could be a few centimeters over here, acetylene could be a few millimeters over here. Therefore, depending on the type of the gas mixture, the measured cell width keeps changing. It also depends on the stoichiometry, because the stoichiometry or the equivalence ratio tells us how much energy is liberated in a particular chemical reactions. This cell structure is not only true for the gaseous explosives, it is true for all detonations, whether it is a solid, liquid, or it could be a gas. Therefore, let us now put together, in the last class we said, well, we found out how much energy is required for direct initiation of a detonation, namely the blast initiation, which we just saw on the board. And if we were to plot a curve between the initiation energy required versus the cell width required, and what was the cell width? It is the width of a characteristic detonation cell. And if I were to plot this particular figure, I find that the initiation energy, that is the energy required for directly forming a detonation, is somewhat linearly related to the cell width of a detonation. As the cell width increases, well, the initiation energy increases, and let us take a look. If I have something like hydrogen oxygen mixture, the initiation energy we said is of the order of some 5 or 6 joules. Well, this is the initiation energy. The cell size is around 1 to 2 millimeters. If I take hydrogen air mixtures, well, the cell size has grown. It has grown to almost like 12 millimeters, and the initiation energy has also gone up to something like almost a kilojoule. Similarly, if I take maybe acetylene oxygen mixture, well, the cell size is extremely fine, around 0.1 mm. The initiation energy is also small, but if I consider acetylene air mixture and inert gas mixture, the heat release is lower, the cell size has increased to something like almost 3 millimeters, while the initiation energy has gone to something like 200 joules. Therefore, depending on the energetics and the cell size, the initiation energy can be related to the width or the characteristic cell size of a detonation. If I consider methane, well, methane in air, well, the energies required are phenomenal, something like we are talking of 10 to the power 6 joules, something like 100 kilojoules, and the cell size is also larger, something like almost like 20 centimeters or so. If I consider methane oxygen, if I consider methane oxygen here, well, the cell size is of the order of something like 3 millimeters, and the initiation is low, energy is lower at something like 300 joules or so. Therefore, for different substances, this particular figure gives the initiation energy plotted on the x axis as a function of cell width, which is, or the characteristic size of a detonation, which is plotted on the y axis. This particular curve also tells us what we discussed in the last class, namely the initiation energy required is very much greater than what is the energy required to form a flame, in which case it was all in terms of millijoules. Now we are talking of kilojoules and megajoules over here, and what we need to therefore note is, maybe powerful igniters are required to directly form a detonation, but we must qualify this by saying, well, I can always form a flame and not a detonation by the ignition energy release, and this flame can subsequently transit into a detonation provided adequate turbulence can be generated upstream. I can form a turbulent flame brush and something like a constant volume combustion or a pseudo detonation before forming a detonation. Therefore, we can tell, well, use of electrical spark for a few hundred kilojoules are difficult, because in nature, whenever we say there is some spill, I can get an accidental spark, I cannot expect to get kilojoules of energy release, I can only get a few millijoules of energy release. Therefore, directly forming a detonation in accidental spills forming explosive gas mixtures are difficult, and in practice I do not have explosive cartridges which really form a shock wave which is going to initiate it, and therefore, in practice the phenomenon of deflagration to detonation transition is more plausible than directly forming a detonation wave. We also see from this figure that when we talk in terms of condensed explosives like solid explosives, the cell sizes are small and the energy required to initiate them are much smaller. We will consider this after a few further classes. Well, this tells us the way in which a detonation gets initiated, about the 3-dimensional structure of a detonation wave, namely a characteristic fish scale or diamond structure, the characteristic size being the cell width, and this characteristic size of a detonation is a very important parameter for a detonation. Having said that, let us go back and see whether something like flammability limits, is there a range of mixtures within which only a detonation can propagate. This data again I took from literature, namely Bull's data, and here I find that if I were to consider a particular, let us say I have C2H6 with air mixture, I have only a narrow region, that means I have lean detonation limits, this is equivalence ratio 1, I find below an equivalence ratio 1 it is lean and a detonation wave cannot propagate. If I consider a rich mixture over here, well, detonation cannot propagate, no detonation in the region to the right of this curve, no detonation in the region to the left of this curve, and only in a narrow region is I am able to get a detonation. If I were to plot on the same curve the flammability limits, the lean flammability limit L will be somewhere over here, the rich limit will be somewhere over here. Therefore, in general the range of the detonation limits, if I were to say lean limit of detonability, rich limit of detonability, the distance between this, that is the detonation, the mixture which supports a detonation is very much leaner, very much smaller than the region which supports a flame. Well, how do we do this? What did we plot in this particular curve? For the flammability limits, we plotted the initiation energy versus the percentage volume by volume, which we said could also be put in terms of equivalence ratio. Well, it is the energy required to initiate a detonation, and you have typical U-shaped curves like flammability limits, but only thing is that the region is much narrower than in the case of flame. What causes this detonability limits? I think we have to take another look at it, and therefore, in the next slide I again go back and show you the 3-dimensional structure of a detonation. You have transverse waves over here. Supposing within a particular pipe or within a particular region I have just 1 or 2 of these cells, that means the cells are very large, let us say, and I have no way in which these transverse waves, when they come over here, can hit each other and create another cell of a detonation. That means the transverse waves, if it rebounds at the wall and comes back, well and good, but you have one transverse wave which hits against the wall, the second transverse wave is also hitting against the wall, and therefore, if I have something like 3 or 4 transverse waves which are formed, then I cannot really maintain the continuity, because I cannot energize these transverse waves and come and hit at the triple point intersection. Therefore, when the number of transverse waves are smaller than some limit, it is just not possible to propagate a detonation wave. In other words, if the number of cells of detonation in a particular region happens to be less than some limit, let us say 3 or 4, the regeneration of a detonation is not possible, because I am not able to get a multitude of transverse waves which keep on intersecting and keep forming these detonation waves, and that is one way in which I can say, well, the limits of detonability are formed. In other words, if I were to go back to the previous slide, all what I am trying to say is, maybe in the region of the limit of detonability, the cell structure is so large that I do not have a number of cells within the region of interest, with the result the transverse waves or the triple points intersect with each other and keep on regenerating the cells, and when regeneration of the cells is not possible, well, a detonation cannot propagate. Well, this is the reason for the detonation limits, and if I were to plot, this is what I showed earlier. I said, well, the limits of flammability are much wider. This is the lean limit of flammability, this is the upper limit, that is the rich limit of flammability. This is for hydrogen oxygen. We said that the lean limit is 4% volume in the volume of mixture, upper limit is around 75. The limits of detonability at a given pressure are between much in a narrower range. Compared to 4, the lean limit becomes 18, compared to 75, the lean limit becomes 60. The reason why it is required is, to support a detonation, you need a large exothermicity, I need a shock wave, I need behind the Mach stem wave which must be sufficiently strong such that chemical reactions can drive it. Therefore, I need more energetics to drive a detonation compared more energetics of chemical reactions to drive a detonation compared to a flame, and that is why the limits of detonation are smaller. Well, this particular point creates one more phenomenon, and that is what I would like to go to the board and illustrate. Let us take what is this phenomenon I am talking of. Let me get on the right side of the board. Supposing I have a pipe, let us say, or a tube in which I am propagating a detonation. This is how we say a detonation propagates. This is the wall of the pipe. Now, a detonation propagates at some steady value, but we said it consists of a series of cells and the detonation propagates through cells. Let us say I have cell like this, I have the cell being formed, this is the diamond cell over here, this is the characteristic width of the cell is the characteristic dimension of the cell. Well, I show the cell by light. There are a series of cells over here, and what is happening? Well, I have within each one I have, let us say, a front over here. I have something like this is being formed. I have another one. I have these transverse waves. If I have the number of cells within this particular dimension, if I have only, let us say, a single cell over here, what is going to happen is, there is no way in which the transverse waves, the transverse waves behind this, I have a wave which is coming, I have a wave which is translating, the transverse wave or the lateral wave gets reflected from the wall, and if the reflection of the transverse wave is such that it is no longer supported by chemical reactions, well, it is going to weaken, and if it weakens out, that means if I have number of cells within the pipe less than some critical threshold, well, a detonation cannot propagate. Therefore, if I say that maybe the diameter of the pipe is, let us say, capital D, if D is of the order of let us say cell size, in practice it is something like 6 to 8 times the cell size, well, a detonation wave cannot just propagate. Another thing which comes in, therefore, but when we had a flame, what did we find? Well, a flame propagates in a pipe and we had something like a quenching distance for a particular pipe. We talk in terms of a critical diameter or the failure diameter of a pipe for propagation compared to the quenching diameter of a pipe over here. In addition, let us say some nice experiments have been done with detonation. If I say along the wall of the pipe I put something like a surface which can absorb the lateral waves. See, waves are going up and down. If at the surface I put a material like let us say I put a low impedance material which takes the wave, that means a wave which comes here, if it is going to be absorbed by it, it is no longer reflected, and therefore, maybe in this case also the detonation wave fails. Therefore, to be able to support a detonation, we need some minimum number of cells within it such that the transverse waves, that is the waves transverse to the front of a detonation, are always present. They can keep on interacting, regenerate more and more of these cells as it keeps progressing, and therefore, the cell size is basic to a particular detonation. Well, this is about propagation of a detonation and we have looked at this, but things are not as complicated as they seem to be. And having said that, let us try to put things together now. We like to work with a simple model of a detonation, namely let us say a one dimensional model. But we said, well, a detonation is not one dimensional. The front consists of corrugations like this. I have transverse waves which are moving, I have transverse waves which are moving, maybe one here, maybe one here, and it intersects, and therefore I form another cell of a detonation, I form another cell of a detonation. Within this, it is the velocity keeps changing, velocity picks up and changing. But we also said if the cell size is small, well, I can if the cell sizes are small, then the variations in velocity are small. I can therefore, under certain conditions, still use my one dimensional model, and within the one dimensional model has a lot of physics in it, and to be able to understand a detonation, let us go back and still presume that the front is not corrugated with multiple shocks, but it is let us say one dimensional. That means I just have a shock as it were, and this shock as it were, let us say, is propagating with chemical reaction. This shock is supported by chemical reactions, it is propagating into a medium whose density is let us say rho 0. Let us say it has the medium has no velocity, u0 is equal to 0, that is the medium is stagnant. Let us say its enthalpy is h0, we just now said its velocity u0 is 0, let its temperature be T0. Behind the detonation wave, that means a shock supported by chemical reactions, the chemical reactions drive the shock, let us say it travels with a velocity v0 into this particular medium which is at rest. What is happening behind the medium? Well, the density has increased, we will work out the density increase in the next class. We will also work out the pressure increase behind the detonation. Well, the temperature is also high because chemical reactions are occurring, the temperature behind the shock itself is high, plus you have chemical reactions occurring. Let us say that the enthalpy here is h. I would like to have a model by which I can calculate the velocity of a detonation. Therefore, to be able to do that, well, the zone of chemical reactions and shock wave is moving as a detonation at a velocity v0. I want to write an equation, and what did we do when we consider a shock wave? We said writing an equation for something which is moving is difficult because my frame of reference is continually moving. Therefore, what I do is I have a picture of the detonation wave stationary, that means the wave is stationary. Well, the chemical reactions are occurring behind the wave, and what does the wave do? Well, the shock wave is there, the chemical reactions are occurring. Let us say that the heat release in chemical reaction is equal to q joules per kilogram. This is the energy which is released in the chemical reactions over here at the shock itself. That is behind the shock, there is chemical reactions are happening, and I am still considering a one dimensional picture. I have the shock front, behind the shock front I have the chemical reactions which are there. Now, instead of this moving, I sit on the wave, that means my frame of reference is with respect to the front over here, and therefore, what is going to happen? Well, the gases approach me because my frame of reference is the detonation with a velocity v0. Here the density is rho 0. Well, it is approaching me with a velocity v0, this being my frame of reference. It is with an enthalpy u0, and let us say the temperature is T0. Well, you know, when the detonation wave is propagating, it is dragging the fluid now with a velocity because it is moving, it is creating some velocity here. Let this velocity be u1. But in the frame of reference of this, what is going to happen? The velocity is going to be v0 minus u1 over here. Let us say this velocity is therefore the velocity with which it is moving is v1, and the condition is rho, h and t. Well, I need to be able to solve this equation for v0 and v1, therefore, I just look at the energy equation, but we have already derived the energy equation for the shock wave. What was the energy equation for a shock wave? Let us first put the picture together. We had a shock wave, we said that the conditions ahead are rho 0, h 0, t 0. We had the conditions behind the shock wave, the shock is the equations were written in the frame of reference of the shock wave, that is the observer on the shock. That means the conditions here are rho, h and t over here. What did we have in this case? We had h, let us put the same notations down, let the velocity be v0, let the velocity be v1 here. We had h plus v1 squared by 2, this is the from treating this as a control volume, is equal to h 0 plus v1 squared divided by 2, that is the enthalpy and kinetic energy is balanced across the particular wave. And why did we do this? We defined a control volume, and in the frame of reference of this we wrote this. And in what way this equation is going to change from here? Well, in this case you just had a shock front, no heat was generated therein, but now I have heat being generated, and therefore, my equation now becomes h1 plus v1 squared divided by 2 is equal to h 0 plus v0 squared divided by 2 plus the energy per unit mass. This is per unit mass, this is per unit mass, per unit mass, per unit mass over here. Therefore, if I were to solve this equation, what did we get? Maybe let us put this equation through. What did we get? From this solution we got gamma by gamma minus 1 into p by rho minus p0 by rho 0 minus, I brought it to the left hand side, I had half into p minus p0 into 1 over rho plus 1 over rho 0 was equal to 0. You will recall this is how we solve this particular equation. And now when I solve this particular equation, what is it I get? Well, I have a term q on the right hand side, and therefore, this becomes is equal to q. Well, this is the governing equation, and what did we call this equation which was equal to 0? We called it as the Hugoniot. And what was the plot of a Hugoniot like? Let's plot it again. The plot of the Hugoniot was p by p0 as a function. We plotted volume ratio, that is rho by rho 0, 1 over rho by rho 0. We said, well, the initial point is p0, that is p by p0 is 1 for the initial point. The value of rho by rho 0 is 1, this is my point 1, and the equation, this when it became equal to 0, we called it as the Hugoniot, or rather the shock Hugoniot. This was the equation which I got. We will call it as shock, we called it as shock Hugoniot. And now what has happened to this equation? I have added a q to it. That means it now you have a shock, instead of having a shock alone, I have shock and chemical reactions. Chemical reactions are giving an energy q joules per kilogram, and therefore, this equation gets shifted up by q, and therefore, I have this is my equation over here, and this becomes what we call as the reaction Hugoniot. Let's qualify this a little better now that we have understood the problem. We are looking not only at a shock wave, any wave which is traveling, and if I have a wave which is traveling, and let us say I look at the conditions upstream and downstream of the wave, I relate it by the Hugoniot equation. Now, when chemical reactions occur behind the wave, some heat is getting released Q, and therefore, instead of having the Hugoniot over here, which I called as shock Hugoniot, I talk in terms of the reaction Hugoniot. Now, what does the reaction Hugoniot, what does it give? It gives states which are behind the wave. That means, it tells what is the density, what is the enthalpy, what is the temperature, what is the pressure behind the wave as a function of the initial condition. That is, the initial condition is P0 and rho 0, which corresponds to the point 1 by 1. That is, from the point 1, the conditions should be along this, because this is the conservation of energy as applied, as a control volume is applied at the point of a detonation, and therefore, my final state should invariably be along this curve somewhere over here, somewhere along this, but I want to know the precise location. All what the shock Hugoniot gave, for a shock, the final states were over here, but how did we get the state for a particular velocity? Well, we had the Rayleigh line, and what was the Rayleigh line? You recall, we had the equation rho 0 squared into V 0 squared is equal to P minus P 0 divided by 1 over rho minus 1 over rho 0 minus 1 over rho. Therefore, we had something like velocity given by the Rayleigh line, and we plotted the particular Rayleigh line for a given velocity. That means, we said Rayleigh line is proportional to velocity, we got the end state over here. So, also when I have chemical reactions occurring behind the wave, well, my final state is along this. Therefore, I should be able to plot a series of Rayleigh lines. If I were to say my velocity with which my detonation wave is traveling is at this particular velocity, well, it could be here. If my detonation wave is traveling at this velocity, maybe it is over here, the slope of the Rayleigh line gave the velocity, or if it is at this, the final state is here, and therefore, I should be able to use the reaction Hugoniot to be able to find out what is my final velocity, provided I can specify the particular velocity. Therefore, let us go forward with this. Let us try to find out whether from the reaction Hugoniot I can find out the velocity and the properties behind the wave, and let's do this problem first on the board before we can follow it using some simple slide point presentations, because I think I should not repeat all the things, because we have done all this in the case of a shock wave. It is just using the additional term Q which really affects your detonation properties. Therefore, let me now put the final figure over here. I have P by P 0, I have 1 over rho by rho 0. This is my initial point. My shock Hugoniot, that is without chemical reactions, is over here. My reaction Hugoniot is somewhere over here. Now, I want to find out what is the final point, what is the state behind this. That means, once I specify the velocity, I will be able to find out what are the conditions behind it. Therefore, let me first put the points down. Let us say I make a horizontal line over here. This is my initial point O. I have a vertical line over here. I also find, well, this particular zone is what, in which initially I have P0 rho 0, that is, this is 1 by 1 initial point. Over here the pressure is higher, because this is 1, this is P by P0 is greater than this. That means, this corresponds to the compression of the wave. If I take a look at this particular solution over here, well, the pressure is decreasing, well, the density is also decreasing, because I am plotting 1 over rho by rho 0. Therefore, this corresponds to the expansion solution. In other words, we find, well, a reaction Hugoniot can give both the compression solution, and a compression is associated with a shock. I have something like an expansion solution, and expansion solution is associated with a flame. We said there is a small drop in this. Therefore, this zone corresponds to a flame or a deflagration. This corresponds to a detonation. In the zone between the vertical line and the horizontal line, well, you find that the pressure has increased, but the density has decreased. How can pressure increase and density? You know, that means in terms of pressure there is compression, in terms of density there is some expansion. Well, it is clearly not possible. Therefore, this zone cannot exist because it gives contradictory. The density gives a contradictory picture, the pressure gives a contradictory picture, and if I were to put it in terms of the Rayleigh equation, I get the velocity to be an imaginary number. Therefore, we find that in practice only the zones, in this zone it is possible, in this zone it is possible, the zone between this is not possible, a region not physically possible. Now, we come back to this particular location. Let us plot the velocity. Well, I have the velocity over here, tangent over here. Well, this gives me the minimum velocity. I also have the maximum velocity for a flame over here, and therefore, let us say the point is over over here, upper point over here. I have a lower point which is tangent over here. Mind you, we have been plotting tangents earlier also. Maybe from the initial point I have the shock Hugonio, I have the reaction Hugonio, I plot this tangent, and therefore, I have a region between this to this, I have a region between this to this, I have a region between this point and this point over here, and between the tangent point over here. That means I get an upper tangent point which is minimum velocity, I get a lower tangent velocity which has maximum velocity, and therefore, is it possible for me to have detonation for different velocities in between these two is the question I would like to ask. Therefore, in the next class what I do is, I will take a look at the different regions of the compression solution, different regions of expansion solution, characterize the tangency points which we will see a steady state detonation is possible under these conditions as Chapman-Jouguet points, and then get the properties of a detonation wave. Well, thank you then.